Okay, I gave a couple of problems to solve at home previous class. I just solve them now. One where I asked you to find the vorticity vector with the velocity field given. So you just have to take the curl, okay? And I asked whether this is rotational. Is it rotational? And what is the criteria for it to become into irrotational? Del cross V has to be 0. This is the solution now. Is understood. What is this cross factor operation? Do divide of 0 minus do z of y to the power 4. Which is nothing but 0. Likewise, j cap also, like both do x of 0 and do z of xy cube both are 0. And k cap, you have do x of y bar, that's 0, minus of do y of minus xy cube. Okay, this is nothing but 3y square x. Minus minus will become plus, so you will get 3y square x k cap. So this is our curl of vorticity vector. And it definitely is rotational because this is not 0, right? Another question I asked you was to, in a Cartesian system, I asked you to plot sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. Where sigma is a stress tensor. These are the tensor components. And I already told you that for sigma ij, I is the direction of surface. And j is the direction of stress. Right. Okay, we'll quickly plot it before we move on to today's class. See, this is a Cartesian system. I'm representing 1, 2, 3 instead of x, y, z. Okay, so direction of surface in this case, everywhere its direction of surface is 2. That means in this direction, the surface will be like this. Then only it will be 2 direction of surface. Because unit normal to it represents the orientation of the surface. Fine. So this will be our plane. And if you look at the direction of stress, that is the J component. So it will be like this. If I'm looking at a point, say here, this particular point, in the direction of 2, it will be sigma 2 2. When the direction of stress is in the 3 direction, it will be sigma 2 3. And this will be sigma 2 1. Likewise, when I do for, and this is the surface. So we'll plot this Cartesian system again. Now, I asked you to plot sigma 3 1 3 2 3 3. Na? So that means the normal should be in the 3 direction, Z direction. So this will be the plane that time. And direction of stress is 3 here. So it will be sigma 3 3. This will be sigma 3 2. And here will be sigma 3 1. Okay. So I will upload all this. Just check whether your solution matches. So today's exam class, I'll mostly be doing some solved examples related to uh, the various flow visualization techniques like streamline, path lines, um, then about stream function, velocity potential. If time permits, one basic problem using the Cauchy's equation. So let me pose the problem to you first. Then I'll give you some time to think about it and then I'll solve it. Okay. So first I'll write the question, then I'll explain what you have to do. Okay. This is the velocity field. And velocity units, as you know, is in meters per second. A is some constant. I'm giving 0.3 second inverse. So x and y have got units of meters. So he has to have units of second inverse, then only it will be meter per second. So there will be 6 subparts to this question. I'll write them first. Okay, so this is the velocity vector ax I cap minus a by j cap, where a is 0.3 second inverse. So first you have to obtain an equation for streamlines in xy plane. Then you have to plot the streamline passing through x naught y naught is equal to 2 comma 8. Determine the velocity at point 2 comma 8. Then the particle passing through x naught y naught, that is 2 comma 8, is marked at time t is equal to 0 to determine its location at time t is equal to 6 seconds. And then velocity of this particle at t is equal to 6 seconds. And finally, you have to show that the equation of path line and streamline is same at 2 comma 8. So I'll give you maybe 5 minutes to solve this problem. Just give it a shot and then I'll come and solve it for you. Yeah. Just refer to the notes about streamline and path line that you'll be requiring those equations to solve it. Taking class now. Oh, after upload the lecture. Okay, Maharashtra. Or fluid mechanics. Yeah, fluid mechanics. Unless, what, sir? Correct. Very correct. Oh, you can take. You have to take. You have to take. Same. 2 hours plus every. Is this comes under like TA? Why you have to the two years you take offset years. Okay. So for offset you take the project. Nice. Yeah, that's nice. No, no. Two has daily during the course year. Course run for 4 months every week. To do it. And this comes under the TA. Yeah. Very good. Don't do it, you won't get money. To get the stipend and everything, your college will be removed from course. Compulsory. They take like this or go to some college and teach. Every week course. Go to some college in the sense that university here. Then that's good. I'll be going there in person. You have to write to the HOD, take their permission, their tickets, their college. Okay. And even a normally. Any college. But I have to come here for my, work, right? And to do work also. You can ask them whether you can take online or not. To take your online option. Online might be okay. For an online, maybe. You're taking for right. It's an NPTEL course. I take it course. Can I keep that here? I'll make it. Here it was a speed before. I put it in here. Okay. Keep it in. Yeah, don't worry. There is a channel. Mama. How much this one cost? So what do you see? There are two of this. One is 34,000 pounds. That's 42 body action. Which one is this? Yes, and before both. But that's why other information is we have to open systems. Which class? What was? Have spoke in next class. They have one line maybe. Have they explained some column dimensions to rotation productivity training and workshop? Your class on it. With margin. How about this one? Relax. Deep. The very classes are right. Yes, yes. Yeah, let me see how the CSS is. So the case of music. The same technique and along with the same technique. Because the same has whole section. What column you are going to explain to Sudarshan? Thank you, Sudarshan. No comments. It's nothing more. See, this Sudarshan be in 1 year, so should also have contact with everybody. You might be talking here, no problem, right? Okay, I hope you solved the question. You have to apply the concepts of streamline and pathline. So I'll just give a brief review of what was covered in the previous class. So basically, the professor talked about visualization of the flow fields. He gave the example of wind tunnel, where they release smoke at upstream and then study the trace the path the particle takes. So again, there are different visualization techniques like streamline, pathline, streak line. So this question uses the concept of streamline and pathline. So I'll just be giving a brief overview of that first. So as is mentioned in the notes, streamline uses the Eulerian approach, which we saw in the previous class also, right? We saw both Eulerian approach as well as Lagrangian approach, and I give an example of each of them. In Eulerian approach, we'll obviously have the substantial derivative concept, while for Lagrangian method, it's a classical mechanics problem. Okay, so I'll just make some notes about this streamline concept first. So the first step here is that in streamline, for a particular instance of time, you draw a space curve first. For a particular instant of time, a space curve is drawn. Okay, say this one is a space curve. So the tangent at any particular point should give you the velocity vector. That is how a streamline is defined. The tangent has to give the velocity vector, meaning that the unit normal that is over here, it represents the orientation of the surface. The cross product of that and the velocity should be 0. So v cross ds should be 0. Assuming v has got UVW components, what does this mean? Let's take a normal cross product. I'm using normal Cartesian coordinates ijk vectors. 2VW ds, the unit normal is either in the x direction dx or dy or dz. So for this to be 0, determinant of this to be 0, just break it down first. I cap of v dz minus w dy plus j cap of w dx minus u dz plus k cap of u dy minus v dx. This should be 0, meaning that each of the components has to be 0, or v dz is equal to w dy, w dx is equal to u dz, u dy is equal to v dx. Fine. So if we combine these three equations, say you divide the first one by vw, so it will be dz by w will be dy by v. Second equation you divide by uw, so dx by u is equal to dz by w. The third one you do by uv, dy by v is equal to dx by u. So when you combine these three equations, you will get dx by u is equal to dy by v is equal to dz by w. So this is the case for 3D. And when you're looking at the 2D plane, you forget the z component. It just reduces to dx by u is equal to dy by v, or dy by dx is equal to v by u. This is the formula we'll be applying in our current problem. Of course, there are other concepts like two streamlines can't intersect. You can just refer to the class notes, because at that same point you'll have two different tangent vectors, which is not possible. The two streamlines can't intersect, and then there can be a flow across the streamline. The next concept of importance here is the path line, which is a Lagrangian approach. A less common approach because it can be a bit more rigorous than the Eulerian approach, but it has got its own strengths. So path line definition is it's a trajectory traced out by a moving particle. Okay. So a particle over here, this is the path it takes. So basically the line traced out by the particle as it moves. That's the path line. As I already explained that you'll have to use Lagrangian mechanics or classical mechanics to solve this. You look at a particle, which is a function of time. Its position is a function of time. X is equal to xpt, y is equal to ypt. Okay. Just as we saw in the last class, you take u as dx by dt of that particle. Fine. Likewise, dy by dt of that particle is v, which can be a function of x, y, and t. Now, with these two, you have to solve the parametric form of x and y. Refer to last class example, or we'll be solving this problem now. Again, I'll be showing what we mean by solve the parametric form. Okay. Okay. Another thing I had forgot to mention in the streamline is that it's not defined in turbulent flow. We are only looking at the laminar cases. Okay. I'll just make a small note of it, and then when we come to turbulent, like that is lecture 6, we'll be looking at that. Not defined in turbulent. Okay, so coming back to this problem, the velocity vector field was given as ax I cap minus ay j cap, right? And a's unit, a was constant with unit of second inverse, and the value is 0.3. So a is 0.3 second inverse. So first we'll obtain an equation for the streamline the xy plane. Okay. So this, as you see, is a 2D flow. There is no z component. Even z does not enter the picture. So it's strictly 2D in the xy plane. So we know the formula. No? We just saw it few minutes back, few seconds back. The equation of the streamline is dy by dx is equal to v by u. Okay. So in this case, what is v? In this case, v is minus ay and u is ax. A gets cancelled, so it's just minus 5 by x. So basically, it's dy by y is equal to dx by x with a negative sign. You integrate both sides. So it's ln y is equal to, when you integrate both sides, ln y is equal to ln of x minus ln of x plus some constant, right? Say c1. So basically, you take x this to the left hand side. It's ln y plus ln x is equal to some constant c1, or ln xy is some constant c1. Or xy is a constant c. So this is our equation of streamline. And can anyone tell what this equation represents? Xy is equal to constant. So it's a rectangular hyperbola, okay? So graphically it will look like this. Okay. So next question was, plot the streamline passing through x naught y naught is equal to 2 comma 8. Right? So if xy is equal to constant, it will be same as x naught y naught, which is 2 into 8 is equal to 16. So our equation, our streamline passing through x naught y naught 2 comma 8, say this is 2 comma 8, this is 2 comma 8. It will just be xy is equal to 16. Next part is determine the velocity at 2 comma 8. So v is 0.3 x I cap minus 0.3 y g cap. At point 2 comma 8, what is the velocity? It will just be 0.3 into 2, that is 0.6 I cap minus 2.4 j cap. Fine. Till here was very easy. Now for the D part, particle passing through x naught y naught, that is 2 comma 8, is marked at time t is equal to 0 seconds. And you have to determine its location at t is equal to 6 seconds. So this is nothing but the concept of path line. You trace the path the particle takes. At t is equal to 0, pass through 2 comma 8. So at t is equal to 6 seconds, what it will take? So use the Lagrangian approach over here. Okay. What's the Lagrangian approach? Lagrangian approach is that dx of dt, dxp of dt is equal to up. Or let us just drop the p suffix and solve it normally. It's understood that we're talking with the frame of reference sitting on the particle. So dx by dt is equal to ax. Likewise, dy by dt is equal to minus ay. Fine. So let us look at this part first. Dx by x is equal to e dt. Integrate both sides. Say from x0 to x and time going from 0 to t. So it will just be ln of x by x0 is equal to at, or x is equal to x0 e to the power at. And if you do for this part, dy by y is equal to minus a dt. Integrate both sides with limits from y0 to y and time going from 0 to t. So it will be ln of y by y0 is equal to minus et, or y is equal to y0 e to the power minus at. So what was the question for us? The question was that the particle passing through 2 comma 8 is marked at t is equal to 0. And now we have to find it 6 seconds where the particle is. So our x0 is 2, y0 is 8. Okay, x0 is 2, y0 is 8. Therefore, x is equal to x0 e to the power 80, or 2 into e to the power a is 0.3 sometime, and y is y0 e to the power minus 80. 8 into e to the power minus 0.30. Now t is equal to 6 seconds. So what will x be? X will just be 2 into e to the power 1.8, and y will be 8 into e to the power minus 1.8. So if you just plug in the values in the calculator, you get, actually I got x is equal to 12.1 meter and y is equal to 1.32 meter. I may have made some calculation mistake, I'm not sure. Just check it out, but this is how you solve it. Coming to the next part, you have to find the velocity of this particle at t is equal to 6 seconds. So what's the velocity vector given us? 0.3 x I cap minus 0.3 y j cap. So this particle at time t is equal to 6 seconds, we already know the location. It's 12.1 and 1.32. So to find the velocity vector, just plug in those values. So it will be 0.3 into 12.1 A cap minus 0.3 into 1.32 J cap. You will get 3.63 I cap minus 0.396 J cap. Okay. Next, you have to show that the equation of path line and streamline is same at 2 comma 8. So at 2 comma 8, we already saw that the streamline equation is xy is equal to 16. Rectangular hyperbola. Now let us look at the path line. So path lane was determined as x is equal to x naught e to the power at and y is equal to y naught e to the power minus at. So combining these two, it's just multiply both sides. Xy is equal to x naught y naught and e to the power 80 minus e to the power minus 80, it becomes 1. So it's just xy is equal to x naught y naught. And x naught y naught you already know it's 2 into 8, so it's 16. So this is the path line approach and this is the streamline approach. You see that both of them reduce to the same equation. So even they look different, but both are same. Just that the frame of reference has been shifted from the particle to some fixed point in space in case of the Eulerian approach. So let us a couple of other basic questions about streamline because like that you may face it in your exam. Velocity field is given as ax square y I cap plus bx y square j cap. A is given as 2 meter to the power minus 2, second to the power minus 1. Just see whether the units are consistent, convince yourself. P is equal to minus 1 meter to the power minus 2, second to the power minus 1. For this, you have to obtain the equation of streamline. Okay, just take 1 minute and solve it before I give you the solution. Okay, I think 1 minute is up. I'll proceed and solve it now. So what is the equation of streamline? It is dy by dx is equal to v by u, or dx by u is equal to dy by v. U is ax square y, where a is 2. So I'll just plug in that here. Dx by ax square y. And what is v? V is bx y square. So x and y cancel out here. You're left with dy by y is equal to b by a into dx by x. b by a is minus 1 by 2. So 1 minus 1 by 2 dx by x. Integrate both sides. So left hand side is ln y. Right hand side is minus half ln x plus some constant. Take exponent both sides. E to the power ln y is just y. E to the power minus half ln x is what? X to the power minus 1 by 2. This constant will become in some other constant c2. So this is our equation of streamline. Y is equal to c2 by root over x. Okay, straightforward. One more example. Here velocity field is given as axy into I cap plus by square into g cap, where a is 2. What will be the unit of a? So this is meter square, and velocity unit is meter by second. So it has to be meter to the power minus 1, second to the power minus 1. And b is minus 6. Similar to this. Unit is meter to the power minus 1, second to the power minus 1. So find the streamline, equation of streamline. Very straightforward. Dy by by square is equal to dx by axy. Y gets cancelled. So it's just dy by y is equal to b by a into dx by x. B by a is equal to minus 3. So it's dy by y is equal to minus 3 dx by x. Integrate both sides, see what you get. So it will be ln of y is equal to minus 3 ln of x plus some constant, say c3. Or y is equal to c4 by x cube. If we know particular x and y, as in the previous case where we had x0 by 0 is 2, 8, you can also find the constant. Say it passes through 2, half. So what will C be? C4 will just be half into 2 to the power 3 or 4. 8 into half, that is 4. And our equation reduces as y is equal to 4 by x cube. Okay. So one more example of streamline before I move to pathline. Velocity field is given as axi cap minus bty g cap. So notice that there is a t component over here, time component. The earlier cases, like it wasn't a function of time or velocity field, like a steady state kind of situation. Here there's a time component also. E is 1 second inverse, b is 1 second to the power minus 2. Find the equation of streamline for any t. So similar to the previous questions, it's just dx by ax is equal to dy by minus bty, or dx by x is equal to a is 1, b is 1, so doesn't matter, both can get cancelled out. So it's dy by minus dy. Integrate both sides, you'll get ln of x is equal to minus 1 by t ln of y, or take exponent both sides, y will be some constant into x to the power minus t. So notice here that we have an equation of a streamline, but it's a function of time. So at time t is equal to 0, it will just be y is equal to constant. the streamline equation. At t is equal to 1, it will be a hyperbola, rectangular hyperbola. At t is equal to 20, it will just be a very fast decaying exponential function. Y is equal to c to the power x to the power minus 20. Okay. Moving on to our next example. Again, let's take a very simple velocity field, a 2D flow, Ax I cap plus 2Ay j cap. A is given as 2-second inverse. You are supposed to find the equation of path line of a particle located at xy is equal to 2, comma 2 at initial position, time at initial instant of time t is equal to 0, and you compare the path line with the streamline to the same point. And just write it in terms of words, make it simpler. The question here is obtain equation of path line of particle located at xy is equal to 2, comma 2 at initial time t is equal to 0. Now compare the path line with the streamline through the same point. So as I already told you many times, path line is Lagrangian mechanics, streamline is Eulerian approach. So let us find the equation of the path line. First, up is equal to axp, that is the u component of velocity. Fine. And what is up? dxp by dt is equal to a to the power a into xp. Likewise, vp is equal to 2 into a into yp, or dyp by dt is equal to 2 into a into yp. Now take xp to the left hand side and integrate this. Take yp to the left hand side and integrate this. So what will you get? I'm not doing the integration steps, it's very straightforward. Do it at your own free time. So when you integrate it, it reduces to xp is equal to some constant c1 into e to the power at, and yp is equal to some constant c2 into e to the power 2at. Fine. So this is our path line. This is how path line is defined. Parametric form of xp and yp. Parametric as in terms of y. So basically the distinction you make between streamline and path line over here is that streamline passes through the point 2, comma 2, and the path line starts at the point 2, comma 2. So that's the approach. Because in streamline, it's an Eulerian approach. You're in some position in space and you're just observing from a distance. Fine. So there it just passes through 2, comma 2. But in Lagrangian mechanics, you're sitting on the particle. Your frame of reference is the particle. So particle, it starts at 2, comma 2. Okay. So I'll just write it in terms of words. So our streamline equation is what? V by U is equal to dy by dx. So just do the same steps, integrate both sides, and we get y is equal to c into x square. And since you know it passes through 2 comma 2, you can find the constant c also. That y naught is equal to c into x naught square. X naught is 2, y naught is 2, so c is equal to half. And our equation is just y is equal to x square by 2. And you compare this with the path line equation that we got here. Fine. Path line was what? Xp is equal to c1 into e to the power 80. Yp is equal to c2 into e to the power 280. So in path line, at time t is equal to 0, it starts at 2 comma 2. So xp is equal to 2 is equal to c1 into e to the power a into 0. And yp is also 2 is equal to c2 into e to the power 0. So c1 is equal to 2, c2 is equal to 2. Fine. And here it is e to the power 80, here it is e to the power 280. So you square this side, this xp, and you divide by yp. So xp square by yp not square is equal to c1 square e to the power 280 divided by c2 into e to the power 280. This gets cancelled out. C1 is 2, C2 is 2, so it's just 2 square by 2 or 2. Or yp is equal to xp square by 2. And that's what we got for the Eulerian approach also. We got y is equal to x square by 2. Here we are getting yp is equal to xp square by 2. Both the equations are equivalent. So in this case, the streamline path line coincide because the flow is steady. Had it not been steady, they would not have coincided. There would have been a time component and all, then that would have complicated matters. So at least in this particular case, a streamline and path line coincide. Okay, maybe take a 10 minutes break and then we look at stream function and velocity potential. Maybe one or two examples related to that as well.
We might get a demo, like sample call tomorrow. Okay. And the person who's coming, yeah, said he will be really one. If I show that to them, they can still understand better. And they also wanted this credit person we have to make that. So we have the entire community once we just clean very clearly. Like this is what we have planned. Then the people will be giving them a sample by the day after. Basically, brings it tomorrow. They may not give it to them by tomorrow. But the day after tomorrow, we definitely give. For this state, they told we can do only this one way second way, but the only company will see difference. Because five so they will find any five markup function. It will be around 8 and that is okay. Just create one fixed cover and a gasket or another sheet of like for me gasket to make it. So to the end and you cover. That is what we do. So we will just this one, this other which has a the same thing we are project. This this is yeah. You have gas ship or like a big ship in 5 minutes. Let's say by the way. That will be gas ship will be it's working with the like vision, like see, really. It's like the people to directions. Like the very dedicated like the speed. Can you avoid it? If you can, if the leader to order take, style, like, what are the things? Maybe ready to target it. In the case of the no, that's okay. You guys are trying to smash more, I think. So that there's no need.
So let's define stream function for 2D incompressible flow. It's defined only for 2D. So U is given as dou psi by dou y and V is given as minus dou psi by dou x. So from the definition itself, you see that it satisfies the continuity equation for incompressible flow. For incompressible flow, the continuity equation is what? The divergence of velocity field is zero. That is dou u by dou x plus dou v by dou y is equal to zero. And the way we have defined in u and v in terms of the stream function, it just reduces to dou square psi by dou y dou x plus dou square psi by dou x dou y, sorry, minus is equal to zero, which is true. And for an irrotational flow, we generally study irrotational flow in conjunction with inviscid flow. Okay, so what's the definition of irrotational flow? The vorticity is equal to zero, or del cross v is equal to zero. In our case, what is del cross v? If I just calculate del cross v here, ijk 2 by 2x 2 by 2y of 2 by 2z uvw. So ours is a 2D flow, so w is equal to 0. So that's only the k component of the spin vector, which is nothing but dou v by dou x minus dou u by dou y. And for that to be equal to 0, dou v by dou x has to be equal to dou u by dou y. Again, going back to the definition of stream function, v is minus dou psi by dou x. So dou x of minus dou psi by dou x is equal to minus dou square psi by dou x square. And dou y of u is dou y of dou psi by dou y. So it's dou y of dou psi by dou y, or dou square psi by dou y square. Basically, what we are left with is, we bring this to the right hand side. Dou square psi by dou x square plus dou square psi by dou y square is equal to 0. And this is the Laplacian. Del square psi is equal to 0. Laplacian operator. Okay, so this is an important result. Not only does the stream function satisfy the continuity equation for incompressible flows, but the Laplacian is also equal to 0. We're not taking irrotational flow. Another thing about streamline is, along a streamline, the psi is constant. So how do you prove it? Okay, see, as psi is defined for a 2D flow, let us take it as some function of x and y. So what is dou psi? Dou psi is d psi is equal to dou psi by dou x into dx plus dou psi by dou y into dy. Dou psi by dou x is minus v, and dou psi by dou y is equal to u. So it's minus v dx plus u dy. And how is streamline defined? Streamline is defined as dy by dx is equal to v by u, or u dy is equal to v dx. So plug that over here. These two get cancelled out and it's 0. Or dou psi is equal to 0, d psi is equal to 0, meaning that when you integrate it, psi 2 minus psi 1 is equal to 0 along a streamline. So psi is equal to constant. And as you can see over here, the flow rate across the streamlines is given by a difference in the values, absolute values of the stream function. Let us plot it over here. This is some stream function psi1. This is I2, and the quantity of the volumetric flow rate in between these two stream functions is just the difference in the absolute values of the stream functions. This has been covered in one of the lectures. You check that out. Likewise, we have another concept for velocity potential, which is valid only for irrotational flows. This is how it is defined. V. V vector is the minus gradient operator of phi. So basically, u is equal to minus d phi by dx, and v is equal to minus 2 phi by 2y. And we can define it for 3D also, 3D case also. But w will be minus 2 phi by 2z. So if you apply the continuity equation now, that is the divergence of velocity vector is equal to 0 for incompressible flow. So it basically reduces to dou square psi by dou x square plus phi by dou x square plus 2 square phi by dou y square plus 2 square phi by dou z square is equal to 0. Or del square phi is equal to 0. Again, the Laplacian comes in, Laplacian operator. Del square phi is equal to 0. So combining this and what we saw earlier, I'll make a general comment. For 2D irrotational incompressible flow, del square psi is equal to 0 and del square phi is also equal to 0. Okay. So this is an important result based on how we define velocity, potential, and stream function. Okay, some examples. The incompressible frictionless flow field is specified by stream function minus 5x minus 2ay, where a is 2 meter per second. So determine the magnitude of flow rate between the streamlines passing through 2, 2 and 4, 1. Very straightforward. So at 2 comma 2, what is the stream function? Psi is equal to minus 5 into 2 into 2 minus 2 into 2 into 2. So it's minus 28 meters per second. Similarly, at 4 comma 1, what is the stream function? It's just minus 40 into minus 40 minus 4. So it's minus 44. So just check out the calculations at your own pace. So what's the difference in magnitude and stream function? Del psi. It's 44 minus 28, that is 16 meters per second. Here the question asks for the flow rate. But here we have units of meters per second and not meter cube per second. It is because like the 16 meters per second is just 16 meter cube per second by meter. So the flow rate is 16 meter cube per second per unit depth, per unit meter of depth. Okay, because we can define a stream function only for 2D flows. So it makes sense, right? We are looking only at the XY plane and not at the depth into the bore. Okay, just application of continuity equation, a couple of small problems. Say there is a velocity field x y square I cap minus y cube by 3 j cap plus xy k cap. Is it compressible flow or incompressible flow? Very straightforward. Likewise, another problem. Velocity field for incompressible fluid is V is equal to ax into ex cap is 3y into ey cap minus 2z the ez direction. So what's the value of A? So just take a minute and solve these two questions and get back. Okay, the first problem is what? This velocity field is given and I'm asking whether it is incompressible or not. Just take the divergence of the velocity field here. So do dou x of this, do dou y of this, do dou z of this. So it's just y square minus y square. So it's 0. Therefore it's incompressible. Divergence is scalar, okay? When you dot two vectors, it's a scalar. The next question, this velocity field is given and I wanted to find the value of A. So again, just apply the divergence operator. It's A plus 3 minus 2 is equal to 0. So A is equal to minus 1. Okay, now let's solve a question where the concept of velocity potential can be used. And from there, we'll also see whether uh, how the lines of constant psi and the constant phi, they're orthogonal to each other. Okay, so that will be the last problem before I wrap up. Next week, obviously, we'll go into the Cauchy's equation, then simplify it to Navier-Stokes. I'll be further elaborating on the Debye-Torres test components, what causes angular deformation, what causes translation, what causes rotation, etc. But that will require some extra time. We'll do it in the next class. So this is the last problem for today. I'm giving you a stream function psi is equal to ax square minus ay square. A is 3-second inverse. Show that the flow is irrotational. Then determine the velocity potential. So the stream function is given to you. From there, you have to show that it's irrotational and then determine the velocity potential. So just take a couple of minutes, think over it, and start solving it. First part is quite straightforward. As we already saw that for flow to be rotational, the Laplacian of the stream function should be equal to 0. Because del square psi has to be equal to 0. So what is del square psi here? 2 square by 2 square of a square minus 2 square by 2 square of ay square. So it's 2a minus 2a is equal to 0. And for irrotational. See. So next part is determine the velocity potential. So since it is a rotational flow, we can define a velocity potential. That follows from the definition of velocity potential. Velocity potential valid only for a rotational flow. So how do we define u, v in terms of stream function and velocity potential? I'll just write it down again. U is equal to minus 2 psi by 2x. V is equal to minus 2 psi by 2y. And U is again equal to 2 psi by 2y. V is equal to minus 2 psi by 2x. Okay, so psi we already know. It's ax square minus ay square. So 2 psi by 2y is equal to minus 2ay. And minus 2 psi by 2x is equal to minus 2ax. We have got u and v. So from here we can plug it to this equation and find the velocity potential. So let's do for u that it reduces to psi is equal to 2axy plus some function of y. And when we apply it for the v component, it is 2axy plus some component of fx. And for these two to be identical, uh, this fi fx term, this has to be constant, right? So basically, psi is of the form 2axy plus some constant. That's our velocity potential. Fine. And we already know that by the definition, we know psi is equal to minus ax square minus ay square. That's given in the problem. So for the next part, I'll show you that the lines of constant psi and constant phi are orthogonal. Let's make that point here. Okay. So, and what happens at constant psi? If psi is equal to constant, d psi is equal to 0, which is nothing but dou psi by dou x into dx plus dou psi by dou y into dy, right? What is dou psi by dou x? It's 2ax. So it's 2ax dx. This is minus 2ay dy is equal to 0, right? So 2a gets cancelled and we are left with x dx is equal to y dy. The slope dy by dx is equal to x by y. Now let us look at the case where psi is equal to constant. That is the velocity potential is equal to constant. So d phi is equal to 0. Phi is already given as 2axy. So it's just 2x dy plus 2ay dx is equal to 0. Again cancel 2a. So we are x dy is equal to minus y dx. Or the slope dy by dx is equal to minus y by x. So this slope, if you take slope 1 and this slope, if you multiply them, say this is 1, this is 2. Slope 1 dot slope 2 is equal to x by y into minus y by x. Y by cancelled, x is cancelled. So it's minus 1. So that tells us that these two lines are orthogonal to each other because when you multiply the slopes, it's minus 1. Hence prove that it's orthogonal. Okay, so that wraps up today's class. I don't want to get into the Cauchy's equation right now because I will need at least 1.5 2 hours to complete that part. So okay, we'll do that next class. I'll start off with talking a little bit about that equation and then looking at Poiseuille flow, the flow between two parallel plates, and I'll try to solve that and let's see what we can do there. Okay, thank you. If you have any problem with assignments, you can contact me. I've already shared my mail and uh, WhatsApp number, so do that. Thank you.